Hello, everyone, and welcome to the Fields Institute for Research in the Mathematical Sciences. My name is Deirdre Haskell, and I'm the Deputy Director of the Institute. We're physically located at 222 College Street in downtown Toronto, and I take this opportunity to acknowledge the land on which the University of Toronto and the Fields Institute operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. As you may be participating from elsewhere, may we suggest that you research the history of your land using the website nativeland.ca. The Fields Institute is a network of 20 universities, federally funded through NSERC and CIHR, provincially through the Ministry of Colleges and Universities, and also from the National Science Foundation of the USA, the Simons Foundation, 9 principal sponsoring universities in Ontario, and by individual generous donors. You may already know the Institute through attendance at one of our programs or events. For those of you joining us for the first time, the Fields Institute organizes a wide range of events related to research in the mathematical sciences, most famously the Fields Medal Symposium, a celebration of the Fields Medal winner. We span the entire spectrum of fundamental, applied, and industry-facing research in mathematics. Fields Magic is an initiative we started several years ago to validate the idea that mathematics forms the core of critical research that can be mobilized to tackle some of today's biggest problems. The programs under Magic bring together researchers from diverse disciplines to progress problem-solving initiatives through collaborative, actionable research. Our first initiative under Magic contributed to pandemic public health efforts during COVID-19 by generating mathematical modeling to inform policy and decision-making at the provincial government level. This work has since expanded to broader public health concerns as the Mathematics for Public Health Network. Our next initiative is focused on climate risk. The Center for Sustainable Development will draw on the mathematical strength of the Fields community, as well as partnerships with a diverse collection of organizations who are involved in sustainability efforts worldwide. We recently partnered with the Waterloo Institute for Complexity and Innovation for a 4-day workshop that engaged with mathematics for complex climate challenges. This was our third climate-related workshop, and it brought together leading climate researchers and applied mathematicians to identify major Canadian climate policy and research challenges for which additional mathematical methods would add value. Today's What the Numbers Say event expands on that work by providing the public with an opportunity to ask the experts questions about climate change and its many impacts. Climate change can be an emotional and controversial topic with lots of inaccurate information in circulation. So it's helpful to orient oneself in what the actual numbers say and take it from there. We've collected some excellent questions from the audience and we'll do our best to address them all. And with that, I'd like to introduce our moderator. Vanessa Schweitzer is an associate professor in the Department of Knowledge Integration in the Faculty of Environment at the University of Waterloo. She's also a faculty member at the Balsillie School of International Affairs. She is director of the Waterloo Institute for Complexity and Innovation, a member of the Waterloo Climate Institute, and fellow at the Cascade Institute at Royal Roads University. Her research has focused on decision-making under uncertainty, namely the problem of near-term decision-making in the context of long-term consequences. She has considered this problem with respect to climate change and long-term energy planning. In these fields, scenarios are often used to make sense of complex and slow-moving problems. Vanessa, over to you.
All right, thank you very much, Dr. Haskell. So what I would like to do now is welcome everyone also and introduce to you our panelists. So good morning or afternoon or evening, wherever you are in the world. I'm sure that this discussion is going to be very fascinating between 3 outstanding scholars. I'm happy to lead today's discussion and we'll be giving the public an opportunity to ask questions directly to the experts that we so often see quoted in the news. Today, we have a truly impressive group where I'd like to start with introducing Professor Madhur Anand. She's at the University of Guelph, and she's a full professor in the School of Environmental Sciences. She is an award-winning ecologist with research interests ranging from theoretical to empirical studies of global ecological changes in ecosystems at regional and global scales, and their implications for human environment sustainability, including social climate systems. She has collaborated with mathematicians, theoretical physicists, statisticians, computer scientists, geographers, and poets. She also served as the director of the Waterloo Institute for Complexity and Innovation from 2015 to 2018, and in 2019, she was appointed the inaugural director of the Guelph Institute for Environmental Research, where she leads a number of interdisciplinary initiatives to help address our climate emergency and biodiversity crisis. She also serves on many granting panels in both the arts and sciences, and on the board of directors of the Rare Charitable Reserve. Professor Anand is an award-winning author and poet at Penguin Random House, Canada. So welcome, Professor Anand. I would now like to introduce Professor Chris Bauch, who is a full professor in the Department of Applied Mathematics, and he's at the University of Waterloo. He is also a core member of the Waterloo Institute for Complexity and Innovation. His research group develops mathematical and computational models of the dynamics of natural systems, such as ecosystems or for infectious disease. The particular emphasis in his lab is on understanding how human systems and natural systems interact with one another, and how this understanding can be used to improve sustainability and human health. His study of systems include tipping points, forest grassland ecosystem mosaics, and forest pest infestations. His research partners have included the World Health Organization, the United States Food and Drug Administration, and the Bill and Melinda Gates Foundation. So welcome, Professor Bauch. And then finally, I'd like to introduce Professor Marek Stasna, who's also at the University of Waterloo. He's a full professor of applied mathematics, and he's presently serving as the Associate Dean in Computing. His research interests span the computational modeling of the climate system from small to large scales. Particular examples include modeling of coastal oceans and lakes, groundwater, as well as conceptual models of past climates like the end of the Ice Age. Professor Statna has a broad experience in how computing works, and specifically high performance computing. He has worked both as a user and manager of these kinds of computational models. And he served as the president of the Canadian Meteorological and Oceanographic Society, gaining a broad perspective on climate-related disciplines. So finally, to tell you a bit more about my own work on climate change, I was a contributing author to the 5th assessment report of the Intergovernmental Panel on Climate Change, which was published in 2014. Back then, I wrote about applications of scenario analysis across global and more localized scales. And I continue to serve on the International Committee on New Integrated Climate Change Assessment Scenarios. The way that the discussion will work today is that I will ask some questions and our experts will reply. If you, the audience, have questions, you can send them in as well through the chat on the right side of your screen. We will then try to get to every question, but it will, of course, depend on time. So I will begin with a simple first question addressed to all our panelists to kind of warm us all up. What I would like to point out is that the climate system is huge and complex. Research to understand how it works and whether a changing climate is dangerous requires mathematics in a variety of fields. So we heard about how some of our panelists focus on natural systems like the atmosphere and oceans, but then also ecosystems are affected, and so are different human activities ranging from agriculture to urban environments. So I'd like to pose to each of the panelists to please briefly explain how mathematical modeling works in the climate research that you do. And I'd actually like to start with Professor Anand.
Sure. So, welcome. Hi, everybody. So yeah, I mean, as a scientist, you pretty much cannot research anything without encountering some form of math. And then when you go on to do modeling, that's even more the case. So I've been working on modeling. I started off working uniquely on ecological models in my career. And so for that, I was mostly studying the response of ecosystems to climate change. So climate was an abiotic factor, right? We know that environment is, ecosystems are, organisms interacting with each other, and they're biotic and abiotic factors in the environment. So climate is one of many abiotic factors. So typically we conceive of that system that way. So the type of models that we use are quite diverse and use a lot of different elements of math. Everything from linear equations, if you're using statistics, to dynamical models, like ordinary differential equation dynamical models. Hopefully that means something to everybody listening. If not, we can talk more about it later. And then we also use sort of numerical / computational models where the equations are not deterministic, but rather include even more dynamical or stochastic components. And we also use agent-based models or individual-based models, as we often call them in ecology, where we're really just they're kind of more on the computational end, where we're just kind of writing out the rules of behavior and then developing different scenarios to see how they play out. So that's a very quick, broad answer, and I don't want to take up too much time too quickly, so we can go back and dive into any of those later.
Yeah, thank you very much, Professor Anand. And so now I'd like to turn to Professor Stathna to tell us about the mathematical modeling in his work.
Thanks, Vanessa, and thanks everybody for joining this panel. I guess my work, there are three different ways math is involved. So for maybe the easiest one to explain is for all the really large computing, the supercomputing, the game is always how do you do something faster? So there are all sorts of mathematical techniques, old ones like linear algebra, and then new ones like different kinds of parallel computing, everything from multi-core to graphics-based units and all sorts of new stuff they invent every year. And the one that's probably closest to my heart is the second one, which is I study a lot of how the atmosphere, the oceans and lakes move. And of course, if you've sort of maybe you're canoeing and you sat by the side of the river and are watching the river, there's all these amazing patterns, right, that nature creates. And how to sort of represent those mathematically and how to visualize them, especially using graphics, is something that myself and a lot of my students find a lot of sort of personal satisfaction in. And I guess the one that's kind of the strangest and the most abstract is climate it's a representation, right? It's something abstract that we as humans have created to try to understand the real world. And when we study climate, we don't want to reproduce nature, right? We want to create a simpler version of it that we can understand. And so something I've been interested in different contexts is what are simple models that help us understand key components of the climate system.
Thank you. And so let's hear from Professor Bauch.
Thanks, Vanessa. Yeah, so my interest in mathematics and climate stems from the mathematical theory of how systems go through tipping points. For example, if you spin a top, it spins, and then after a while it starts to wobble. And when the wobble starts, the collapse is coming, right? So it turns out that many systems go through this type of behavior. These kind of signals emerge before it tips over. And we have a beautiful mathematical theory that describes how systems go through tips. And it turns out that it's many of the same patterns and features appear, whether you're talking about a top or water freezing, or the Gulf Stream collapsing, for example, or epileptic seizures for that matter. So I'm interested in taking that mathematical theory, supercharging it with artificial intelligence, and trying to understand climate tipping points.
So we have quite a distinguished panel of, looking at the climate in different ways, using different math to do it, and also looking at different behaviors of the climate system. So another question that I'd like to ask is whether you would say there are some uniquely Canadian aspects of climate modeling. Professor Stathna, would you like to start?
Sure. Thanks, Vanessa. So, Canada's a vast country, right? But in terms of where the population is, one uniquely Canadian problem is that our population isn't where the country is, right? So there are vast parts of the country that have almost no people. So the experience with the climate system is actually limited to, this thin strand within 150 kilometers of the US border, basically from east to west. So one problem that maybe a lot of us don't think about is the question of permafrost, right? So vast sections of Canada's north have all the land underlain by frozen soil. And as the climate warms, a lot of that will melt. It'll melt in unusual ways, right? It'll change the way that the land kind of interacts with the atmosphere. You might have large landslides, you might have changes in vegetation. And I mean, it's not a 100% uniquely Canadian problem. In Finland and Russia and northern parts of Norway would be interested in the same things, but it is a almost uniquely Canadian problem. And then I guess the other one that's close to home is if you're sort of in the Greater Toronto area, you kind of look out on Lake Ontario all the time. We have these amazing inland seas, right, called the Laurentian Great Lakes, and that a lot of us live near, but perhaps don't think of them very much. So they have some analogies to the open ocean, which a lot of the world studies, but they have some important differences, and they make for a particularly Canadian aspect that a lot of us have vacation experience from, right?
And then is there anything that anybody would like to add? I wasn't sure, Professor Bauck, if you had any thoughts.
Yeah, I think that covers it. Yeah, we do have this very strong latitudinal gradient from all the way down to the GTA to the Arctic Circle. And so as the climate changes, we'll be seeing a shift in the range that some species can persist in. And I think many Canadians are interested in that question of as the temperature changes, will species be able to migrate or live in the warmer areas that are further north than they're used to? That's a big open question that's very relevant to Canada, as well as countries like Russia and Finland.
Yeah, I love that you both kind of brought up ecosystems in your answers, which is great. I would just maybe then add, maybe not so much on the sort of geophysical side, which has already been covered excellently by my two panelists, but maybe on the social side as well, with respect to some of the unique and diverse cultures we have in Canada, including for our First Nations. So, and the reliance on certain types of ecosystems and the sensitivity to changes that are going to arise. So that's maybe not unique to Canada per se, but it is something that is quite significant. So yeah, I would just add sort of considering truth and reconciliation and resilience and social equity, which is really a global thing, but we do have some unique challenges and responsibilities in Canada.
Thank you, Professor Anand. And what you're saying is reminding me of how when we started off the whole event for today and Dr. Haskell was introducing everyone, Dr. Haskell had made reference to an event that was jointly sponsored by the Fields Institute and the Waterloo Institute for Complexity and Innovation. One of the speakers that was there mentioned that from her perspective, and she was a social scientist, so this was part of why she said this. She said that she felt like climate change was just as much a governance problem, or maybe even more so a governance problem than a technology problem or a problem of the natural system kind of acting up. And so this recognition sort of feeds into one of the questions that we actually received before the event from someone named Carrie Landry, who asked, once you've presented your models, what are some of the biggest barriers to getting them mobilized into climate action? It seems as though the science and math are clear, yet sufficient measures aren't taken to mitigate impacts. How do you, as climate scientists, deal with the frustration of explaining what will happen, yet not seeing enough done to prevent disaster? Professor Anand, would you like to start?
Sure. Yeah, so this is something that we do come upon quite a bit as scientists working in this field. As I mentioned, I am an ecologist. I've been working on climate change modeling more recently, and some socio-climate modeling more recently, exactly to try to address this challenge of how do we get our scientific knowledge more taken up more by policymakers. But initially, I would say that, like as ecologists and as scientists, right, as you all know, we've understood a lot about the relationships between human and the climate system, like for centuries. And then in terms of understanding the impacts on ecosystems, we ecologists have been demonstrating this for many, many decades. In fact, my colleagues and I co-wrote the first sort of textbook called Climate Change Biology. And it was all about the responses of ecosystems and species, largely non-human, but like basically our biodiversity that we live with, to climate change. And that was published, I think, back in 2009 or something like that. But more recently now, I've just become more and more interested in the human side of things, the human component, right? Because we do have a vast amount of scientific knowledge in terms of what causes climate change, what are some of the impacts of climate change. Really, we do know a lot, and a lot of it is very well collected and integrated into the various IPCC reports over the years. But still, right, it's not being, we are in a climate emergency. So I started to work collaborating with Chris on some modeling having to do with just how do we examine not just the negative impacts that humans can have, but the positive impacts that humans can have in this issue, in this problem, because really it's our only way out. And so that's one thing that scientists can do. I mean, not every scientist is going to be able to do that or want to do that, but that is something that you can do as a scientist. And so integrate that type of study. And indeed, you mentioned social scientists earlier. And so I think coupling, an interdisciplinary research, frankly, between scientists and social scientists and others can really help to bridge the gap between science and society. Literally, like if natural scientists work with social scientists, that's the first step, right? And it's a big gap still in research. So that's something that I'm trying to do to help bridge that gap. And then, of course, there's interfacing with policymakers more directly through working with NGOs, working with governmental agencies. So we do a lot of that also. As researchers, we often co-produce and develop research questions to address policy. So that can really help because then there's like a feedback loop that is established there. Maybe I'll stop for now, but I could come back to giving some more specific examples later. I'll let others answer.
Yeah, that about covers it. Since we collaborate together, we have a very similar perspective on the matter, and we collaborate to develop these models of social climate interactions that are hopefully going to help us understand pathways to stimulating more action.
Well, maybe I could
Go ahead.
I mean, why is it so hard, right? Well, it's hard for a couple of reasons, right? I mean, ideas are new and they take a while to take root, right? Climate change is not something that's been kind of discussed in modern terms for hundreds of years. It's been discussed for decades. There's a certain amount of, we expect, and historically have expected a lot of our politicians to be quite literate about the law, right? You have a lot of lawyers traditionally go into politics. We've not necessarily had the same expectations of scientists, and we don't even have kind of systematic programs like they do in the US for bringing scientists to Congress, to have scientists come to Parliament, right? There used to be a science panel that reported to Parliament, and then that was dissolved at one point. And I guess the third point that kind of merits saying is there's a pretty large amount of interest that works against climate change, right? There are people who have strong economic interests in doing the same things that they've always done to continue to make rather large sums of money, and they can spend much more than any scientists on advertising campaigns and sort of other ways to move public opinion. Now, having said all that, I think actually we've done remarkably well, because this issue, and I think both Kristen and Anand said it, people are really well-meaning, and one of the things you do as a scientist, you're constantly challenging your assumptions. Is my idea right? You know, do I have this all wrong? Should I start thinking in a different way? And it really does come down to talking to different kinds of thinkers than yourself, and coming up with new angles and new ways of looking at this stuff. So I think people shouldn't give up hope. It is a hard problem, but actually, given the short amount of time in which we've had kind of this effort going on, we've done okay. It's just that now because it's this accelerating process, right? Now it's really important that the rubber hits the road in the next half decade or so.
Well, thank you very much. That was good that, that we're kind of like opening up, talking both about that interface between what the numbers say, but then also that society interface, right? And like deciding what to do. And Professor Anand said something in her remarks that I thought was really interesting, that I think would make sense to kind of move to unpack further. And it resonates with one of the questions that we received from students at W.H. Morden Public School in Oakville. So we actually received a lot of questions from these students, and it was very exciting to see how engaged they were with the topic, and the questions were excellent. We jotted down a few to answer, and one of them reminded me of something that Professor Anand was saying in her reply. Let's see here. So it's from Susie Wen, who is 13. And Susie asks, is it possible to use climate change or its effects to our advantage, such as a source of energy, maybe while mitigating negative effects on the environment? So yeah, I guess I'll start with Professor Anand to see if there's anything that you wanted to add, because you said something about how you're trying to think about the positive things that society can do responding to climate change or figuring out how to respond. So yeah, I wasn't sure like how you think about it. Does it kind of match this question that's being posed by Susie? And even if it's a little bit different, I thought this would be a good time to explore this question with the panel.
Okay. Hi, Susie. Hope if you're watching. Yeah, I don't know. I mean, I don't have an engineering background, and I do feel like if we had an engineer here, do we? I don't know. They would have some pretty interesting answers to this question of what you can do. And I mean, there's a lot of sort of ideas out there about how to engineer things, but I would just give a couple of examples of how what we do know about how our response as humans to the main factors of affecting climate change are, of course, greenhouse gas emissions. But there's a number of secondary things as well, that sort of indirectly lead to more greenhouse gas emissions, agricultural practices, deforestation, et cetera, right? So, I mean, all of that does sound bad, right? In terms of it's not to our advantage to continue to do those things in terms of the climate. But then I would perhaps put out a couple of examples, and then maybe the students could think of more, or we could others can add more of where, some of the activities that we are going to do to mitigate climate change, i.e. reduce our greenhouse gas emissions, will be beneficial not just to climate, but to other aspects of our lives. So I would kind of think of it more in those terms. And so one example that we actually have just recently worked on a project with another collaborator at the University of Waterloo, Rebecca Sari, is a study that looked at modeling and math applied to the synergistic meaning when two things come together and are more than the sum of its parts, more positive, and the synergistic effects of reducing greenhouse gas emissions and reducing air pollution. And where those two problems sort of come together, because air pollution is another very big problem in many parts of the world, not so much in Canada yet, although we are having the forest fires right now, creating air problems. But in other parts of the world where there's coal burning, etc., and greater population density, there are a lot of really bad air pollution problems. So, some of the mitigation techniques that we're going to put forward will help with other aspects of human health, like air pollution or just general. We've done studies on, diet, even changes in diet, and how a more climate-friendly diet could be actually more healthy for humans, right? So I would like to think about it in those terms. Of course, you could also give other examples like, yes, there are going to be places on Earth that will see higher temperatures and therefore longer growing seasons, right? So that is true, but that's not going to solve all of the environmental crises that we're facing, right? So we can't just sit back and say, well, that's going to be better. The scientists have done those sort of more complex, integrated studies where they look at not just one factor in isolation, but several factors simultaneously. And there's no question that we do have to mitigate climate change.
Are there additional thoughts from panelists?
Yeah, I really. Go ahead, Mark.
Yeah, no, it's okay. You go.
Okay, sorry. Yeah, I really like this question because I started to think, well, are there actually, things that we can take advantage of as the climate changes? And I couldn't think of anything off the top of my head. So, for example, it's going to get hotter, but it's not going to get sunnier, so we can't get more solar power. It might get windier at times, but these big wind turbines are designed to behave in a certain range of wind speeds, and they can't be too low or too high. And as the Earth wobbles more, the range of winds at which we can get energy from them will decrease. And it would be great if we could just pump the heat somewhere, but where do we pump it? Well, we can't pump it into the Earth because the Earth is hot enough, is even hotter than the surface if you go down far enough. And we can't pump it out to space because that's the whole problem. It gets absorbed by the greenhouse gases. So I couldn't think of, in my very naive, 5 minutes treatment of the question, how to take advantage of climate change. But like Mother said, it's really a question of mitigation and adaptation. How can we minimize the impacts? It's not really a question of harnessing it in some way, as far as I can tell.
Yeah, so I mean, I agree with what both panelists said. I mean, I guess I'll go back to something what Professor Anand said. The fundamental good thing that could come out of climate change is that humans learn how to put the price on common things like air and water, right? So if you think about things that have taken us a long time to get better at, right? That's one we just haven't, as a species, done yet, right? And so if we come up with some, diverse but generally accepted set of rules for putting a price on clean air, clean water, some acceptable level of greenhouse gases in the atmosphere, then that will be something good that'll come of it. You can come up with engineering examples. I mean, maybe the best current example is how much cheaper solar panels have become because of the interest in renewable energy, right? So the ones on the roof of my house are about 20 years old, and they would have cost about 20 times of what the current state of the art would be. And the new ones would be much better than the ones on my roof. So there are definitely concrete engineering solutions. But like Chris said, it's not like they're coming out because of climate change. They're coming out because of the work of humans to try to kind of ameliorate what's happening with climate change. If you think about the effect on ecosystems, the unfortunate thing about climate change is that the vast majority of ecosystems are quite helpless, right? So if you think about coral being susceptible to bleaching when you have ocean heat waves, right? That's an example, right? I mean, who doesn't love snorkeling over coral? But those little suckers can't go anywhere when that heat wave comes, and then they're just kind of bleach out and die out. So
Yeah, and thank you for all of those reflections. One thing that I thought was maybe worth kind of like pausing for a moment to unpack, just in case people in the audience are not fully familiar with how Professor Statna referred to pricing things. When I was working on my master's of environmental studies, this was a long time ago, but I nevertheless recall that sometimes people were just really offended by this idea of, what do you mean put a price on clean air? But it's actually the fact that we have not put a price on it is why people will just sort of think like, oh, it's no big deal. You know, if I pollute, whatever, you know, the atmosphere is so huge, it doesn't make an impact. And so, you know, we have like this long history of the Industrial Revolution, you know, over 100 years, 200 years of this kind of behavior. And because it's gone on for so long and there was no price to, you know, having carbon dioxide or other greenhouse gases just get dispelled to the atmosphere, that's part of why we have the problem that we have now. So it would actually be useful if instead of putting a price on the widgets that you can make from your factory while it's like releasing this greenhouse gas pollution and only pricing the widgets, right? That's the only thing that was sort of encouraging certain behaviors, right? So now if people realize, oh, actually, we want to value the clean air, we want to value an atmosphere that's not overloaded with greenhouse gases. We need to figure out how to sort of develop those market signals. So I just wanted to like unpack that a little bit more. Yes, Professor Anand.
I'm so glad you brought in that word value, because I was going to say that. So I would much rather use the word value than price, because you know, we also ecologists, we've been doing that for a little while now. They're called valuation of ecosystem services, and you know, climate. Well, ecosystems can provide lots of different values to society and humans. One of which is indeed climate mitigation, right? As we know, forests, peat, bogs, etc. But you know, there's a little bit of a difference, and I won't go into it too much now, but there's a difference between putting a price on something and saying that we value it. So, you know, these are actually some of the things that we explore in some of our human environment models, where the economics is one of many components to what we call a utility function, or what economists call utility functions. And so we do want, you know, take into account some of the other factors with which humans use to ultimately make their decisions and behave, right? So we are, and so yeah, we kind of need a new mathematics of sustainability, a new mathematics of eco economics and ecosystems, etc. And so if you look at some of our recent studies, and I hope some of you will, and if you need to know where to find them, I'm sure that the Fields Institute will direct you to them. You will see just how we do that, right? How we include not just economic valuation, but other types of valuation.
Thank you very much, Professor Anand. And you're sort of your fingers on the pulse, I think, of some of the audience members, because there was a comment that recently came in from Brynja Kohler asking, how does the panel think that education needs to change in order to prepare students to address the challenges in our climate crisis? And I think that there are maybe two ways to be interpreting this question. One you sort of hinted at with your remarks about we sort of need a new mathematics of sustainability. But I would also like to broaden that question to reach out to the young audience members, the mathematics that they're learning now in the K through 12 system. What is the further mathematics that we need to learn and we need to develop in order to address climate change?
Well, if it's okay, I'll start with this one. So I've given lectures in a program called Math Circles here in Waterloo. Oh, geez, it's been almost a decade, I think. And I've done it, grade 9, grade 10, grade 11. It comes in different packages. And I guess one of the things I find, I couldn't sit still when I was in school, and I find the same sorts of things that drove me crazy then drive me crazy now. So much of our mathematics education is formula based, right? It's about this is the right answer and this is the formula, right? So there are important principles of mathematics. Everybody should know how to specify the slope of a line, maybe the intercept, the difference between a line and a parabola, and things like that. But really, once you get past these very basic facts, so much more of math could be exploration based, right? So coming down, having access to simple computational devices, because one of the things with the climate system, unlike a lot of kind of physics, especially, right? Because physics and math have this multi-hundred-year history of intertwinement. Climate stuff is new, and a lot of climate stuff doesn't come in a nice, tidy formula, right? It comes in data packages, and then, as Chris mentioned before, you start getting into AI and things like that. Those are fundamentally data-based techniques, and so I think getting exposure to that from a young age and losing that kind of timidity that we have in mathematics class, I think that would be a huge advancement, not just for climate, but I think in general for education.
Yeah, and I think a lot of the new mathematics is actually existing mathematics that's applied in a new way, and to use this to tackle climate problems requires interdisciplinary work, and also sitting down with policymakers and asking them what questions are of interest to them. So as a mathematician, I can't sit in my office and just do mathematics on some sheet of paper and then publish it and I'm done. I should really be talking to policymakers or stakeholders and saying, well, what problems are you facing? What are the questions you're interested in? And then developing research questions from that, involving them throughout the whole process. And that forces me to learn about the stakeholders, learn about climate systems, and apply the existing mathematics in new ways. So I think that's, in terms of how that comes out in education, it would be again through interdisciplinary education. So not just learning calculus, for example, but learning some applications of calculus to physics or chemistry at the high school level. Kind of an integrated curriculum might help solve that.
Yeah. I had a couple of thoughts, like in listening to my co-panelists here, and given our involvement with Wiki, the Waterloo Institute for Complexity and Innovation, I think kind of more awareness of complex systems and their dynamics would be kind of neat to introduce earlier on into our education. I don't know. It'd be kind of neat because that's the kind of thinking in a way that is required to understand some of our contemporary problems. I mean, probably it always was, but we've just been getting better at understanding complex systems and what some of the sort of minimal constructs are for these. And like, just to give you an example of what I mean, everybody's probably heard of chaos theory by now. If not, I think they even mention it in Jurassic Park, which is probably also a really old movie now that you guys probably haven't even seen. But when I was studying, I came across chaos theory when I was in graduate school, like way past high school or anything like that, but probably because it was only coming to become it was only kind of getting more popularized, I think, even though it was sort of discovered in the 60s. When you look at the origins of chaos theory, just look it up. It's a fun thing to read about. That's a kind of thinking and a kind of dynamic that's really important to understand systems like climate, and the impacts that we can have, and the importance of very small changes that can have global effects. It's a nice idea metaphorically, but it also is basically a mathematical idea. And some of the original studies in chaos theory were mathematical models of the weather system and of climate, Lorenz's equation of climate, right? So I would encourage you to go and look up Lorenz's equation of 3 variable, very simple model of weather/climate, and that could be done in high school, I think, and studied. And it's just like certain types of thinking that I know sometimes I think we may be underestimating, but I'm not a teacher and I don't have the job and responsibility of being a teacher, which I know is really hard. But maybe some, opportunities, right? Opportunities for youth to get involved with climate modeling would be amazing. Fields Institute.
Yeah, we're full of good ideas today. And so I again, timely comments being made about, if we look at kind of the origins of a lot of key concepts in understanding complex systems, they actually came from studying weather systems, weather and climate. And we did receive a number of questions that were basically asking about these two systems and how they are related to each other. And actually some of these questions actually came from the students as well. And so I think that I will invite Merrick to start with answering some questions about these two systems, where one of the questions we have is from Dennis Kulichenko, who is 13. And he asks, how can we better predict how climate change will affect the weather forecast? And can we adjust it using those predictions?
Okay, thanks, Dennis. It's a cool question. It's a very hard question, actually. So one of the things to remember is that when you're trying to study the climate, you're trying to study lots of things all at once, right? So you're trying to study the atmosphere, the oceans, maybe a little bit of ice thrown in there, some ground, some trees, and all the rest of that stuff. So that ends up, you write down some rules for this, and then you have to put it into a computer, right? And how much detail you can specify depends on the size of your computer. So in the space of my lifetime, remember when I was a little kid, my dad used to sort of sort his punch cards at the breakfast table because he was going off to do a big calculation, right? I now have 1,000 times more power than that very fancy computer from the 70s in my phone, right? So then in the same way, the computers that I program on, right, allow me to maybe do a better job at telling me about the climate on smaller sized boxes. So maybe I can take one neighborhood in Toronto, right? I could tell you about the climate from Parkdale over to Mississauga or something like that. And with each couple of years, right, because computers have been getting better and better, we're able to kind of get to smaller and smaller scales. You have to remember, when you think about climate and us, we're small, right? And the world is very, very big. So if you want to talk about weather, of course, those are questions like, do I need an umbrella on my way to school or to work, right? When you talk about climate, in a perfect world, you would talk about lots and lots of weather and then kind of average it out to tell you something about, the overall pattern of how weather is changing. So we can't quite afford to do that, but we're getting close. So there are models where the climate model and the weather model are kind of becoming one. So that would be the perfect answer. The answer most of the time is a process called downscaling, which is really difficult to describe, but it's a way to try to incorporate some of the kind of the noisy parts of weather into climate models. And I think that's, there are whole doctorates and even higher studies than that for people pursuing that. And I think it's a field that's kind of really come into its own in the last 20 years. Now, what do we do with all that information? That's an interesting question. So one of the things that we try to do more of is provide seasonal predictions, right? Sometimes we're quite good at it, or we do it for farmers especially, and sometimes we're not very good at it, right? So one big problem, if you've gone on vacation in the recent past, there are these large amounts of seaweed washing up around Florida and the Caribbean. And we don't really know how to predict these giant sargassum blooms, right? So I think the game plan is going forward is take the stuff that we kind of know about the world as a whole and bring it down to the scales that affect us as sort of one person at a time.
That's really fascinating, because I hadn't actually heard that perspective before, Professor Sasna, with respect to like how to approach the future of climate modeling, and instead of like, thinking of the whole system and trying to downscale it, actually maybe trying to direct the attention of the models down to particular locations to better understand the impacts. That's very interesting. There was a related question, both something that we've had in real time. It's asking about extreme weather, and we did have a question that was asked in advance from Janine Gong in grade 7, and I think that these like extreme weather questions are closely related. So Janine asked, can you explain the science or math behind extreme weather, and how it can be so cold on one day, but then on the next day really hot? And then I guess if you have any comments about just unpredictable weather that are kind of maybe some like interesting cases that you've come across in your work, if folks could speak to that. I think that Professor Bauch maybe has some thoughts to start us off.
Yeah, sure. So Janine, you've probably experimented with putting food drops in water, and then you kind of watch the plume spread throughout the water, and the clear water's here and the dyed water's there, and they're right next to each other. And if you give it a small spin, you'll get some whirlpools, and then the dye will be in one band, and then the clear water will be another band, and eventually it'll get mixed up. But for most of the time, the Earth's atmosphere is like that intermediate stage where you've got these big whirls, masses of air moving across the Earth, and they have some might have higher pressure, some might have lower pressure, and they're kind of running up against each other and moving north and east in the northern hemisphere, for example, on average. And so as a result, because the Earth's atmosphere is always being turning over like this, you can have cold weather one day and then very hot weather the next day as the system moves through your local area. And in terms of the extreme weather events, I would kind of approach it from a different perspective from, many climate scientists. I would take this tipping point perspective, and it's really just a hypothesis at this point. But one way you could interpret extreme weather variability or increasing weather variability is as kind of the wobbling of the top, because we know that before a tipping point comes, systems wobble, they become more variable, and you see these more extreme fluctuations before the tipping point is reached. And again, that's universal to ice melting, water freezing, or epileptic seizures, etc. So it's possible that the increase in extreme weather events is kind of this wobbling, which is occurring in many of our climate systems before a tipping point. But that's still just a guess or a hypothesis at this point.
And I suppose something that I could add to what Professor Bauch just mentioned is I am not a paleoclimate person. I did my postdoc at the National Center for Atmospheric Research in the United States, so I was rubbing shoulders with all kinds of interesting climate researchers. And on this note of saying that you have this hypothesis of like, when we see more and more variability in extreme weather events, might that possibly be like a signal or something that is like indicating that the system might flip into something else? And I know that there are people who study, right, like ancient climates millions of years ago, and the Earth has gone through like very big variations in terms of being like hothouse Earth and then like Ice Age Earth or Snowball Earth, like all of these kinds of things are part of Earth's history. And so there are readings of how the planet was when it had like 1,000 parts per million of CO2 equivalent in the atmosphere. Right now, we're a little over 400 or 410. And so in terms of saying that, like, oh, could the Earth have other states? If we're getting warmer and as we're having higher concentrations of greenhouse gases, I think the answer is yes. I think that that's like a non-controversial thing to say. But yeah, an open question of, as we see, more extreme weather events, does that mean something? What does that mean? Is that an indicator for some sort of tipping point into something else? But I think that that's part of what, the research that still has to be done. So thank you.
Could I just add something?
Yeah,
quickly?
please do.
You made me think of something, especially for the students, but I mean, really for everyone. You don't have to go that far back to get massive changes right here in Ontario, right? So 18,000 years ago, big chunks of Ontario were under ice. And you can go around to fields and see all sorts of interesting leftovers. The landscape just around Waterloo here, there are these little hills, right, that were all scraped, the Waterloo moraine scraped by the retreating glaciers. There are giant boulders left in fields called erratics that you can see all around Ontario. You can go up to the end of Spadina Street and kind of climb the little hill there near Casa Loma, and that was the shore of one of the mega lakes that formed behind the retreating ice sheet. So really, old climate change is all around us, and you can get it's kind of a spooky perspective when you think about it, but it's not that old, right? It's only 18,000 or so, less than 20,000 years, and you can experience it yourself.
Yeah, thank you. Yes, Professor Anand.
I just might add something sort of on what we perceive as extreme events. So yes, like I really appreciated and learned a lot actually from what my colleagues have and what you have said about the climate itself in terms of these extreme weather patterns, but I was also thinking about what we're seeing more and more in terms of like the implications of those extreme events for humans, and in terms of our ability to respond and adapt, and how some humans around the world and some populations are going to be in a better position to do so than others, largely due to mobility issues, just like the coral, just like the plants. But I was thinking of the example. So this is an example where, like, some extreme what could be some extreme weather patterns or events, on their own might not be sort of problematic, but combined can be quite catastrophic. And the example most recently that I was asked to speak to, just on to media on, was what the floods that we saw in Pakistan last year. So some of you may recall, and if not, you can go back and check the news, that there were some very, very serious, catastrophic and large-scale floods in the country of Pakistan. And so the journalist, or the TV anchor, whoever the person was, asked me, well, what caused those floods? And I said, well, it was actually a combination of things. So normally floods is just too much water, right? So yes, there were, scientists had predicted, or climatologists had predicted greater monsoon. Monsoon is a kind of rainfall pattern that's very typical of tropical regions. Greater rainfall. But that alone was not what actually caused the flood. It was a combination of that with higher temperatures and generally in that same season, which cause, because a lot of Pakistan is a mountainous, there's a lot of mountains in there, and there's a lot of glaciers and just general like snow-covered mountains, that caused melting of that snow, which then, caused more input through rivers into the river network. And so that in combined, right? So higher temperatures, more extreme temperatures, and more extreme rainfall came together. And because of the fact that the population in that country lives generally in those floodplains, because those are the most agriculturally fertile areas, left them the most vulnerable to those floods, right? So it's these combinations of things that are already quite. We're seeing a lot of pretty disastrous tipping points, I would say, for human systems. And yeah, sorry, I don't want to leave on any kind of terrible note, but just to say that in isolation, these extreme events might be something that we can respond to, but it's often the combination of factors, and it's the rapid rate of change, right? So it's the rapid rate of change, the rapid onset of these highly variable patterns that are making it very difficult.
Yeah, and thank you, Professor Anand. That was really illustrative of how, with the reason why, you often hear the phrase climate crisis being used in the media. Part of why that terminology is used is because it's not just about the physical climate system. It's also things like our built environments. What kind of climate do we build those environments for? And are they going to be resilient to climate change that we're witnessing at the moment? And there are open questions for how much more climate change will we sort of let happen, versus if we'll be taking ambitious action to try to steer the ship, if you will say, steer the ship of the economies and the kinds of technologies we use. And you also mentioned earlier that there are dietary decisions that we can make that have implications, right, for how much greenhouse gases, overall are, each of us being a little raindrop, how big is this ocean of climate change getting based on our small contributions and whatnot. And so we did actually have some questions that were related to things like the built environment. And so we had two questions. One we received before the event, and then another one that sort of came in during the Q&A. I'll first start off with saying what the question that we received previously from Michael Freed was. So Michael asked, what are the most effective mitigation strategies that can get built, such as into actuarial planning for cities, particularly higher risk cities that may be on, it says here on water, perhaps referring to coastal areas or areas that are maybe prone to flooding. And asking about the math that supports those strategies. Something that I would like to add that was, again, kind of a quick question that came from the audience here. If you're aware of any books that you would recommend about, the built environment, its vulnerability to climate, also make a book recommendation. So I think that Professor Statna might have some thoughts to kind of kick us off on that. But I wanted to add, also think of a book recommendation if you have one.
Ooh, okay, I'll try to do those in parallel. I'll think about a book while I'm trying to answer. Okay, well, I mean, I guess the primary thing I would say, and this has kind of been a topic that's bubbled up a few times in the conversation, is that doing something about climate has to do with climate, obviously, but it also has to do with what we do as people. So one of the, I think, best things cities could do is upgrade their infrastructure, right? So maybe in Southern Ontario, anyway, one example that's been really well documented by the Intact Centre here in Environment at Waterloo is sewer systems, right? So quite a few cities, our cities aren't ancient, right? But they are not cities that were built sort of the last decade, which means we have infrastructure like sewers that sort of might be decades old. And it's not a particularly glamorous thing to invest in, right? But trying to make sure that a sewer system is more modern and has all sorts of different solutions, everything from standard engineering solutions like better pipes to things like taking those awful concrete sort of open sewers that seem to run through a lot of cities and turning them into more naturalized spaces and wetlands that can absorb a lot of extra water if there's a flood coming. I think that's a really wise investment, right? So I think it should be context dependent, and of course, different societies around the world have different challenges as far as climate changes. But I guess that would be my. A lot of times, climate change is presented like we have to do crazy things right now, and maybe some stuff really does require drastic action. But a lot of the things we could be doing as a mature, rather wealthy nation in Canada are things like upgrading our infrastructure. And I guess in terms of book. And I'm in the middle of Jeremy Rifkin's Resilient, and I'm trying to remember. It's got the word resilient in it. Somebody will remember the title, but he's published a lot of books about kind of thinking about economic systems and climate systems, and I think that one's got some really interesting ideas in it.
And then are there others? And I was just rereading the question. I guess it doesn't necessarily have to be a book, maybe just other things that any panelist would recommend that people look up in order to understand more about built environments and how they could be climate resilient.
I think Mother is putting something in the Zoom chat that maybe I don't know if they can see it on YouTube.
Yeah, I put it in. I put it in because yeah. So I just have a couple of books I can just recommend. So one is a book called How to Be a Climate Optimist by Chris Turner. That has a number of examples of sort of, I don't know, success stories, I guess, like are things that have been done worldwide. So I put it in the chat. I don't know if it can be shared out to the YouTube world, but it just won a big award as well. How to Be a Climate Optimist by Chris Turner. And then I have another suggestion, which is not so much engineering solution oriented, but it's not even really scientific per se, but it's an anthology, a wonderful anthology called The World as We Knew It, Dispatches from a Changing Climate. And it's these two the two editors sort of put out a call to some of the best writers of our time to of all genre, including, science fiction writers, journalists, etc., and fiction writers even. So about sort of, presenting some thoughts and like sort of very, very, we were talking about the downscaling of the climate system to very local. Well, this is like downscaling the human experience to very specific local responses. And so it's really neat that way because it really transverses it. There's contributions from many different parts of the world and very different kinds of systems. And I think it's really nice to be able to talk about it, right? And to hear about it. So those are my two book recommendations. Yeah.
All right. Well, this has been a really engaging conversation, and I think that I received a note that we'll have to go ahead and wrap up here. But this has been a great panel. I do want to thank all of our distinguished panelists, as well as the Fields Institute, for hosting this event, and of course to everyone who attended and sent in their great questions. We got to almost all of them. So if you still have questions, make a note of our names. Maybe you can reach out to us. We love talking about this issue and helping others learn about it. So I think I'll go ahead and turn things over to Dr. Haskell. I wasn't sure if I saw Dr. Haskell come online. I wasn't sure if she was wanting to wish people off or if I should do that. Didn't mean to surprise you.
Thank you so much. Thank you to all our panelists for really interesting and thoughtful answers to questions and all the ideas that you have. And thank you to all our audience for joining us today. And we hope you'll be able to join us on another episode of What the Numbers Say. And indeed, let us know what you'd like to hear about.
Bye-bye. Thanks, everyone.